Okay, let's go ahead and start the class. It's already 5:30, and one announcement before we start the class. Homework 4 is posted. Okay, and to appreciate your guys' attendance, let's do this. Can you tear up a paper? Just write your name as on the paper, all of you, right? And you will get bonus points. I see we have 2 people on YouTube. Send an email right away. And to get the bonus point. Yeah. And whenever you're done, just give me the paper. Yeah, and the 2 people. It is going to be next Monday, which is Monday, April 5th. I'm positive it's April 5th. But next Monday. So it's 7 days, 5:30 p.m. There are 8 questions on the homework, all of them from chapter 4, different parts of chapter 4. And yeah. Is there any questions? No. Nothing. Okay, let's keep this on board. Is there any one of you who has seen the homework at all? No. Okay, make sure to check it out. Let me know if you have any questions. Most of the problems we have already talked about in class, all of the problems. And you shouldn't have any problem solving the homework problems. Okay, today we are going to finish chapter 4, which focus on the two-dimensional analysis, two-dimensional analytical analysis of the airfoils. And hopefully we will finish the discussion on chapter 4 in the thin airfoil theory and move on to the three-dimensional effects and move on to talking about the wing analysis. Okay, the last thing you want to talk about, in general, today's lecture is a somewhat light lecture. We don't have that many equations and that much mathematics. We will watch a couple of movies, so I guess different lecture, if you will. The last thing you want to talk about when it comes to chapter 4 analysis is the pressure drag. I think Paul hasn't. Have you presented your name? Yeah. Just pass the line. Okay. Just yeah. Thank you for coming in early. For those of you who did. We want to talk about the pressure drag. We have already talked about the friction drag. Friction drag is there because of the shear stress between the wall or the airfoil. Let me write it down here. Or the airfoil. Right? And we actually we calculate the friction coefficient. We don't really calculate the shear stress at the wall. If we calculate the friction coefficient, we can have different flow regimes, laminar to turbulent. There can also be transition from laminar to turbulent. We already know all of this. We already know how to do the calculations. Thank you. You already know how to do the calculations. And yeah, we have already solved one example from the friction drag. We have discussed this indefinitely. But how can we analyze pressure drag? The first thing you want to know when it comes to pressure drag is why do we have the pressure drag? Why is this type of drag present on an airfoil, right? And we have talked about it briefly, right? The idea is when you have flow on an airfoil, because of the friction, because of the viscosity, because of the importance of viscosity, you will get the presence of Barre layers, right? At some point inside this Barre layer, your pressure gradient, so dp dx, is going to push the flow in this direction, opposite to the flow direction. So pressure gradient is going to become dp dx, opposite to the flow. Is it true? I think so. Is this the correct spelling of opposite? I think so. Opposite to the flow. And this is the thing we call adverse pressure gradient, right? Adverse dp dx. Okay. Because of this adverse pressure gradient, we are going to see the formation of vortices or flow moving in the wrong direction, right? And this is something we call flow separation. So flow field, the real flow field, which is fluid particles moving from this location to this location, has separated from the airfoil. Okay? Right? Flow is moving in this direction. This is going to cause a lot of problems in general for our flow. But the main one is its effect on the pressure. Let's take a look at pressure gradient with respect to x. This is pressure coefficient. So pressure coefficient on top of the airfoil. We start with a very high value, P minus P infinity, right? Divided by Q infinity. That's your pressure coefficient. Then it goes to a minimum location, and then it comes back up, right? Then it gets to a positive value. As you can see here, the gradient, which means the slope here, is positive, right? The slope here is negative. The slope here is positive. This negative slope is very consistent with the flow, right? Flow moves from high pressure to low pressure, right? But on the other side, flow is moving from, we are going to have flow separation. So flow is going to move back, right? So what does it mean for the forces in this direction, in the direction of the drag? What does it mean? It means there is some part of the flow that is pushing the flow against pushing the airfoil against the real flow, right? So we will, I mean, anchors. What do you mean by that? Will the drag increase? The drag will increase. That's the idea. So, and this increase in drag is all attributed to pressure drag. So pressure drag is there or increases because of the adverse pressure coefficient. And we are going to experience huge drag when we include the effects of viscosity and we see the flow separation. Okay, so yes. How can you repeat your question? But you had, I think your question had two parts.
What's the difference between like this, like when the flow separates and pressure drag versus when it separates and friction drag?
So flow separation doesn't, when the flow separates, the contribution only goes to the pressure drag. Friction drag is there because of boundary layers, right? So it doesn't necessarily, your flow doesn't necessarily have to separate for the friction drag to exist or to be dominant. Does it make sense? Okay, yes.
So the drag force is generally the direction in the positive direction if you draw an axis.
That's right.
But the adverse pressure gradient, you said that it pushes the airfoil forward. So would the net effect somehow reduce, or that the boundary?
Not the net effect of the, okay. So the total pressure difference between the front and back of the airfoil is going to be different. You're actually going to see two figures that is going to make it more clear. Right? The net force is going to be in this direction. That's true. That's
Dominant, and this effect that pushes the airfoil forward direction, it is there, but it's
it is actually not going to push the flow in this direction. It's going to push the back of the flow down, right? That's the problem. Maybe I shouldn't have said push it front, but that was my mistake. I shouldn't have said it. Okay. Okay. So where were we? Josh, right? Josh brought up a good question, good point, and this is something we need to talk about a little. So the idea is we have two main parts of drag: friction drag and pressure drag. Friction drag is there because of the presence of boundary layer. Let's say we have a flat plate. It doesn't really matter what is your velocity when the flow approaches the flat plate, but you will have a region at which your velocity goes from 0 to the free stream velocity, v infinity, on both top and the bottom. This effectively happens because some of the momentum, fluid momentum, flow momentum is going to be lost because of the presence of the flat plate, right? So this momentum usually dissipates at heat, right? Or any other kind of energy dissipation methodology. So that is going to be the source of friction drag. But let's say you are approaching, your flow is approaching at an angle, you will definitely get the boundary layer, right? But because of the adverse pressure gradient, at some point, okay, let me actually put it this way. So in the boundary layer, we said the velocity is distributed like this, right? It starts from 0, go up. But after the separation point, your velocity is distributed like this. So some part of the fluid is going in the other direction, right? So higher pressure here, lower pressure here. If this happens, if you have a separation point, you are gonna experience pressure drag, right? If not, I mean, you will have the friction drag whenever you have the boundary layers present. Okay, is this clear now? Okay, that's good. But one important point remains true, right? That you need to keep in your mind, that if we don't consider the effects of viscosity, we won't be able to see this flow separation and higher pressure drag, and we won't be able to see the boundary layers, right? So viscosity is the main driving factor here, viscosity itself, which is going to cause two types of drag, pressure drag and the friction drag, okay? Does it make sense? Okay, let's see. So, as I said, if we don't include the effects of viscosity, we are not going to see the real flow separation, real flow separation. But the question is, what is going to happen to the flow when we do not include the effects of viscosity? When the flow is inviscid, when we assume the flow is inviscid. The idea was inviscid flow means that we have to neglect viscosity. That was the idea. What do you think will happen to the pressure distribution over the airfoil? CP or pressure coefficient distribution. What do you think will happen to this? Again, the idea here, that's a non-realistic type of thinking, right? So you essentially have to run a numerical simulation to see the results of this, because in real world, there is no way you can just remove viscosity, right? So what if we run some sort of a numerical simulation, CFD simulation, and get the results of it? What will happen to pressure? Okay. The flow field is going to be different, which means that for the inviscid condition, your flow is always attached to the wall. There is no momentum loss. You're going to have the same velocity, not the same velocity, but the same magnitude of velocity everywhere on the walls, everywhere else as well, right? And for the viscous flow, in which we include the effects of shear stress, of course, we are going to have boundary layers, and you may have a region of separated flow. So let's think about this. Let's talk about this amongst ourselves. The idea is the real pressure distribution looks something like this. That's the real pressure distribution for the viscous case, right? What do you think will happen to this pressure distribution, pressure coefficient distribution, over the top of the airfoil when we don't include the effects of viscosity? Do we have any ideas, any guesses?
Would it be like straight lines?
Straight lines. Like this. I mean, it won't be a straight, but what will happen is we will see some unrealistic values for pressure, right? So our pressure is going to look like this. So very, very huge, I guess you want to say, drop in P minus P infinity, in the pressure coefficient. So we will see some unrealistic values for pressure coefficient. And what does it mean for the pressure distribution on top of the airfoil if you want to order for lift and drag force? Is this. Let's say I'm going to use this pink chalk for the inviscid flow and the green chalk for the viscous flow. So When this happens, when you have very, very low pressures, right? What does it mean? Very, very negative pressures. When you have very huge deviations, it means that essentially your whole system is going to be messed up. But eventually, the results is going to be like this. Your lift is going to keep increasing and increasing and increasing and increasing as you increase the angle of attack, and your drag is not going to increase that much. But in the real case, what you have here is actually a huge contribution of the pressure drag if we have already surpassed the stall condition, and a huge drop in the lift situation. So just a qualitative analysis, very short, brief qualitative analysis of what is going to happen when you include the effects of viscosity, what is going to happen to your pressure when you include the effects of viscosity. Okay? And eventually, this flow separation, let me ask you, actually, we have talked about this in the previous lecture. What will happen to your airfoil or to the flow as you increase the angle of attack? What was the condition? You remember we had the CL versus alpha. It had a peak, right? We had a maximum CL that happened at that alpha. What was that peak called? A stall condition, right? This pressure drag directly contributes to the stall condition. Okay, and it's something that you wanna talk a little further. We want to talk about a little more. We want to go in a little more detail. So CL versus alpha. This was your maximum lift coefficient, right? And then you will see a drop in lift. And it happens at a specific alpha. This region, this point is called a stalling point. And the condition itself is called a stall condition. Okay. We want to see what are the different types of stall conditions now. We want to see what are the methods we can actually employ to change the stalling point, to change the angle of attack, or to increase the lift, if it's even possible to do so a little more. But before moving on, let's see how we can calculate the stalling velocity. So we want to see what will be the speed. What will be the speed here? So that's a very good question. We will definitely have the adverse pressure gradient, right? But the problem is going to be that that adverse pressure gradient is not going to cause flow separation. That's because of the model cannot see any flow separation because there's no viscosity. That's why you will get very unphysical results. And it's actually very, I don't want to say very difficult, but in a very high angle of attack, when you have surpassed the stall conditions, running this type of simulations is very problematic. It will diverge the simulation. It will diverge. You have to make a lot of assumptions. You have to help the solver a lot, and you have to do a lot of relaxation. So yeah. Okay. So the stalling velocity. Let's talk about how we can find the stalling velocity. What do you think we should do here? We want to find the stalling velocity as a function of forces, lift force, the CL coefficient, the lift coefficient, and like the density and all of those things. What comes to your mind when it comes to the calculation of the stalling velocity? How should we approach this problem? How can we get an idea on what the stalling velocity would be? It is not equal to 0, though, is it? The lift slope. So what Joshua is telling us is that the lift slope is going to be 0, which is correct. So, but how can I connect this to velocity? Your observation is 100% true. How can I connect this to velocity? So again, the question is, how can I find the stalling speed during cruise conditions? Which effectively means that this is going to be the maximum speed you can fly at, right? That's the cruise, that at the cruise condition. Okay, let's take a look at the cruise condition a little further, right? What is cruise condition? Let me ask you this. I'm pretty sure you already know what the cruise condition is. A steady flight, right? What does it mean? You don't want to change the elevation, right? That's one thing. You want to keep flying at a specific elevation. You don't want to change it. You don't want to decrease it. You don't want to increase it, right? And so we don't have a. Let's look at an airfoil again. Let's say it is flying at a specific angle of attack. We have lift, weight, drag, and thrust, right? These are the 4 main forces that we are really concerned with. Okay. What is the force balance during cruise condition? What do you think the relationship between the forces, these aerodynamic forces, should be to maintain a cruise flight? Lift equals weight, right? Because you don't want to have any excess or in any direction, right? In y direction. But if your weight is higher than lift, then you will decrease, your elevation will decrease. If your lift is higher than weight, then you will start pitching up, right? That's the idea. So for cruise condition, lift has to be equal to weight. Okay, so that's one statement we can say about the cruise condition. But again, let's go back to the original question. What is the stalling speed during cruise condition? And to answer that question, let's see how did we define the force coefficient? How did we find the force coefficient? What was the main definition here? Lift over 1/2 rho v infinity squared multiplied by the area, right? Okay. What will happen to this equation during a stall? In a cruise condition, in general doesn't have anything to do with the stall. Your lift will be weight, right? That's the idea, to maintain the cruise condition. But during the stall specifically, you are going to experience your maximum lift coefficient, right? And your velocity is going to become the stalling speed. So if you rearrange this equation, your stall velocity is going to be, during the cruise condition, is going to be equal to 2 multiplied by weight force divided by rho S, span area, maximum CL. So this is one of the few equations you're going to see in this class, the stalling speed during the lift condition. The next step is to see what are the different types of stall. We are going to see in a flight condition. So there are 3 different types of stall: trailing edge stall, leading edge stall, and flat plate stall. So trailing edge stall is the stalling condition when your stall, your flow separation starts from the trailing edge, right? As you increase your angle of attack, it will move up. Okay? So the separation point starts from the trailing edge, then it will move toward the leading edge as you increase the angle of attack. That will be your trailing edge stall. Okay? So based on this explanation for the trailing edge stall, what is the leading edge stall? What is the leading edge stall? The flow separation starts from the leading edge. That's true. Okay? So let's actually not have it like a bond area. But how is that possible? Right? Like if you think about it logically, the flow separation, the adverse pressure gradients, is going to start from the leading edge, and as you increase the angle of attack, then it will move up the airfoil, if you will, towards the leading edge, right? How can we have a leading edge stall? And where does it go after our airfoil has stalled from the leading edge? Leading edge stall is a sudden phenomena. That's the key here. So trailing edge stall is a gradual phenomena. It starts from the trailing edge, move towards the leading edge. Well, leading edge stall is a sudden phenomena. So you don't have the flow separation, don't have it, don't have it, don't have it. At one point, at one angle of attack, all of the flow on the airfoil is going to separate. So what do you think this means for the CL versus alpha plot we have here? What do you think this means for this? That the flow doesn't separate, but suddenly all of the flow on the airfoil, on top of the airfoil, will separate. it will not necessarily a piecewise function, but you will see, but you are moving in the right direction. So you will see a very sharp decrease, right? Because there is sudden flow, all of the flow separates, right? So all of the force balance is going to be messed up suddenly. Okay. What is a flat plate stall? Flat plate stall is a stall that happens on a flat plate, on very thin airfoils. It usually looks like the leading edge stall in general, but it stalls earlier compared to the leading edge stall. And also, in general, flat plates will give you less lift coefficient, a smaller lift coefficients. And the reason they stall earlier is because very sharp edges. Again, your flow sees a flat plate with sharp corners, right? It doesn't mean that this flat plate has to be a sharp flat plate, but it's so thin that your flow sees a flat plate with very sharp corners. And we actually have a definition. Your thickness has to be 2% of the chord for your airfoil to be considered a flat plate. Is there any questions? Okay. So let's compare these three stalls. Which one do you think will give you the highest lift coefficient? The maximum lift coefficient. I didn't have to. Let me redraw this. Which one do you think will give you the highest lift coefficient? And the highest lift coefficient is going to be the lift coefficient at the stall, during a stall, right? That's the maximum lift coefficient you are going to get. So whenever you hear the word the maximum lift coefficient, that's the lift coefficient during the stall. So essentially, this means that I'm asking you to tell me which of these types of airfoils is going to give you the highest stalling lift coefficient. The leading edge stall, yeah? Because the flow separation happens later, right? So the lift coefficient can go a little higher. So the leading edge stall usually looks like this. Very sharp decrease, okay? But the maximum value of the lift coefficient is very high. But the trailing edge coefficient, you have a very gradual, there's a very gradual nature to it. So the stalling, it starts somewhere here, and it goes for a longer time. So trailing edge stall, I'm using the yellow color for this, and the leading edge stall. Okay. So what do you think is the value of the maximum lift coefficient for a flat plate stall compared to those two? Is it higher? Is it lower? Or what is it? Flat plate or thin airfoil?
Probably lower, but still has like a sharp decrease of the leading edge stall.
It is lower, that's true. But what was the reasoning? What did you?
It probably has like a sharp decrease, like the leading edge stall does, like afterwards.
Mm-hmm.
Like
That's correct. That's correct. So essentially, all of the flow is going to separate from the flat plate. But why is the lift coefficient lower? I actually mentioned this very briefly when I was talking about it. Sharp edges, right? What do sharp edges do? They are going to facilitate the separation, right? So the separation doesn't really happen. I mean, it happens because of the adverse pressure gradient, but your sharp edges, sharp corners are going to be helping the flow separation. You know, we had a discussion about tipping the flow to turbulence, right? So you have some sort of a mechanism there on your airfoil to tip the flow. These sharp corners are tipping the flow to separation, if you will, okay? So your maximum is going to look like this compared to, let's use another color, thin airfoil, very lower maximum. Okay? And we have already talked about the stalling speed. What will happen to your stalling speed when your maximum lift coefficient increases? Let's say we keep everything else constant. We don't change the weight, the structural weight. We don't change the maximum lift coefficient. We don't change the density or the span area, but we change the maximum lift coefficient. What will happen to the stalling speed? It will decrease. Yeah, exactly. I mean, you can see it from the equation. But if you keep the stalling speed also constant and let the weight change with a higher maximum lift coefficient for the same stalling speed, you can carry more load, right? You can have higher weight on your airplane. Okay, but the question is, how can we change that stalling point? How can we increase the lift coefficient at that stalling point or increase the angle of attack at which the stalling happens? Okay, so the main mechanism behind the stall was the flow separation, right? So you want to change the flow separation, right? We also have another mechanism to increase the lift. What was that? We actually have discussed this in the beginning of this chapter. Think about it. One mechanism to delay the stall is to come up with some sort of a design that delays the flow separation, right? Or makes the flow separation a little less dominant. But we have another mechanism that can increase the lift coefficient, the maximum lift coefficient you can get out of an airfoil. What is that? Anyone? Area. You effectively are going to change lift, the total force, by changing the area, right? The coefficient, we define the coefficient to make it independent of area, right? And velocity and all of those things. What was this whole chapter before today? What was this whole chapter about? Then we were not talking about drag. We were always talking about lift, right? And how to calculate lift, right? Okay. So what were the two different types of airfoil we analyzed? We divided our analysis to two different types of airfoil: symmetrical airfoil and cambered airfoil, right? Cambered airfoil is going to give you negative zero lift angle of attack, right? And also higher lift coefficient. That was the idea of the cambered airfoil. So one mechanism to increase the maximum lift coefficient you are going to get out of your system is to increase the camber, right? So there are two goals here. We either want to come up with a mechanism that is going to help us delay the flow separation, okay? Or we want to increase the camber mid-flight. Right? How can we do that? We have a couple, I don't remember who, but we have a couple of graduate students who are working on this as their project. Flaps and slats, right? Introducing flaps and slats, right? So these are flaps and slats are called the high lift devices. Flaps and slats, and there are a couple of more mechanisms. So by introducing this, we will be able to play with the flow pattern on the airfoil, which means that we can delay the flow separation, and we can also change the camber. One of the most traditional types of the flaps and slap is the trailing edge flap. Let's say this is your airfoil. At the end section, you are going to introduce a mechanism that is going to let you change the shape here, right? So you can either move it down or move it up and change the shape of the airfoil. What does this do? Let's say what happens when you move this flap downward with a negative theta, negative angle. What happens to your, the positive is considered in this direction. So positive theta, negative. Just for the flaps, trailing edge flaps. What will happen to your lift versus CL versus alpha when you change the angle in this direction? Again, your airfoil is like this, then it will look like this, right? With a positive trailing edge flap angle. We had two main mechanisms, right? What is one mechanism we are working with here? Which one we have chosen to work with here? What are we changing? The camber, okay? So what do you expect should happen? To lift versus CL versus alpha. Let's say this is the symmetrical airfoil. So we start at 0, and this is CL versus alpha. What will happen with a positive angle, which essentially means that we are increasing the camber, right? Your CL, your maximum CL, is going to be higher, right? So positive theta. And if you move this trailing edge flap in the other direction, your maximum is going to change. Okay? So you can obviously see, you can see that even with a very simple mechanism, we can change how the airfoil behaves at different angles of attack. But this is not the only mechanism we have. This is not the only high lift device mechanism we have. We have the leading edge slats that are, let me actually use the Who steals these wipers? I don't get it. Okay, we also have the leading edge slats that are installed at the leading edge. We have This is the. We also have something else called the leading edge dupes. All of them are flaps and snaps. Different types of flaps, different types of snaps, and they all are going to change your camber. But how can we change the flow pattern? How can we use the second mechanism that is available to us to change the flow pattern? Let's actually discuss this. Let's do this. Since there are only like 2 or 3 students who contribute to the discussion, we are going to start from Ty, and I want all of you to chime in. So the question is, we already know how to change the camber. Using the trailing edge flaps, changing the angle, your camber is going to change. There are some automatic models out there that change the shape of the wing completely. So it's not just a camber at the end. You will get a, let's say this is your symmetrical airfoil. Your airfoil is going to change shape and become like this, right? We had someone who wanted to become a faculty here who did that research. It was an interesting research, but we didn't hire the person, the guy. Okay, so, but the question here is, what do you think the mechanism is that is going to help us change the flow pattern on the wing?
Can you add like a sharp edge?
Sharp edge.
Like a triangle at the end?
So something like this?
I meant like on the wing itself, kind of like to force the separation to start.
We want to delay the separation though, right?
Okay.
Right? Because the separation means that we are nearing the stall, right? So, and the stall condition is not a very desirable condition. You're going to lose control, you're going to lose elevation, your force balance is going to be messed up. So we want to delay the separation.
I don't know. I don't know now.
Okay, that's all right. Not knowing is a good answer too. What was the name again? Wyatt. Okay. So creating a sharp edge like this. Oh, flattening it like this, right? Okay, that's an. I don't know what I assume. It will definitely increase drag because you're putting a flat surface in front of the flow, but it may delay the flow separation. I don't know. We have to study that. That's an interesting idea. That's an interesting conclusion from the earlier discussions. But it's not the best way of doing this because so we want to make changes on an airfoil, right? During flight. So you don't want to like change the shape of your leading edge during flight. It will mess up the things a lot. Okay?
I was trying to think of something, but I'm not sure if it makes sense. Like have a flap underneath the airfoil that comes down on the to just change the size of the camber.
So like this, or the same thing as we had before, something like this.
Well, yeah, I mean, but kind of like not on the trailing edge. I don't know.
So separated from the wing.
Right.
Okay. I had one person, Trevon, had his hands up. An inflated. So you want to like have this type of the leading edge? Is this? So you want to increase the thickness? Is that it? Huh. That's an interesting perspective too. But increasing the thickness is going to make the flow separation just gradual, moving from a sudden separation to a gradual separation, right? The retractable thing, something like this is something we will discuss, okay? John?
Trying to change the flow, right?
You want to change the flow pattern. Yep, that's the idea.
So, could you do something similar to the trailing edge to the leading edge, just like increasing the curvature somehow?
Well, how would that only affect the, not only, how would that affect the flow direction directly, flow pattern directly, right?
I'm just thinking that if the angles change, that the flow is going to be different.
That, yeah, that actually that can happen too as well. Okay, so increasing the, like adding a leading edge slap then. Shelby.
You add like, I guess like a retractable piece in the back, kind of like you were saying, but I'm not sure about the shape, I guess. But.
Okay. So we have 3 votes for a retractable shape at the back. Okay. Wings. So like this.
I don't know how you would show it, I guess, in this kind of form, but like literally coming off the body like a wing, that would change the flow, because then it would also have, what do you call it, adverse flow behind it.
But you are going to induce flow separation with that way, right?
Yeah.
We want to delay the flow separation. We want to come up with a mechanism that pushes the flow on the airfoil, right? That's the idea. Whose turn is it? Paul.
I was thinking you want to try to change like the chord length essentially. So if you had like swept wings, you change like actively change the sweep angle of your wings, so you have like a different chord length exposed to your flow direction.
That's for the 3-dimensional effects, right? We will talk about it later. That's what 2-dimensional changes can you make to an airfoil?
I feel like we still have to do something with the chord length, try to change that somehow.
Chord length.
Yeah.
So whatever we do is going to change the chord length anyways, right? Because increasing the camber, like stretching the airfoil, right? But how would that, think about it this way, how would like stretching the airfoil, right? How would that change the flow pattern? How would that reduce the flow separation?
So it increase it wouldn't matter. So you need to like reduce the chord.
That's the, okay. That's one way of looking at it. But then you are reducing the span area, right? Which means that you're going to have lower lift, total force, right?
Could you do something to the bottom of the wing? Or like
What?
Like add something in the front that's like kind of like the first piece you have there, like continuing down to the front of it.
Oh, like it, something like this?
Yeah.
Okay. I guess so. We will actually talk about this as well. Thank you.
What if you ionize the air towards the front of the wing and use magnetic fields to manipulate the flow velocity?
Oh, that's a very creative way of looking. Thank you. That was a very interesting thing. That's actually something they already do. It's called the dielectric barrier discharges, right? So you are going to induce plasma on top of the airfoil, which is going to add a source term to an Navier-Stokes equation. So it is going to push the flow down. It's going to, yeah. Thank you, thank you. That actually, that I did some research during my master's on the dielectric barrier discharges. Yeah, so using plasma ionization. That's definitely one way of looking at it, but it is a little out of the scope of this course. Do you have anything to add to that one? Okay, so let's move to.
Perhaps you could add like a class of leading edge instead of like going out to the tail edge.
Is it a retractable or is it
Like a separate one.
separated from the body? Okay. That's it?
Yeah.
Okay. Joshua. That's all right, no worries. You want to change the flow pattern, not necessarily the camber. I mean, camber will probably change anyways, right? Whatever make. But how should we change the flow pattern? Okay. So it's something like this, right? Okay. Jacob, do you have anything more?
Honestly, I don't really understand the diagrams and how there's different bodices outside of the original one.
Which diagram don't you understand? Which diagram do you understand? Don't you understand?
All these teardrop things, I thought they represented something going through the wind.
Yeah. So you're talking about these. You don't understand these. We'll talk about them. Let's actually talk about them. That's the idea. Okay, so most of you, or some of you, talked about this mechanism. Let's say this is your wing, this is your airfoil, just to make it a little more understandable. Then you have a mechanism. It's a retractable thing, right? So at some point, this will start moving away, which means that you are going to introduce a hole here, right? What will happen here when you're introducing a hole? It will act like a suction from the bottom, right? Because we have high pressure on the lower surface. We're flying higher pressure on the lower surface, low pressure on top surface, right? So high pressure, low pressure. So we are going to induce some flow in this direction, okay? So even if your flow has already separated here, you are going to force it to stick back to the wing, okay? But we can actually, by introducing something in front, so let's say this is your wing, and then you release whatever that is in front to move forward, you are going to push some streamlines to stick to the airfoil. That's how you affect the flow pattern, right? You are going to minimize the effects of viscosity by reducing the body layer thickness and effectively reducing the flow separation or delaying the flow separation. Yes.
On that little piece that you have above, would the flow separate on top of that? It would just be minimal.
On top of this?
Yeah.
We will definitely have flow separation on top of this, but the contribution of that separation is not going to be that much, right? So you're not adding to the problem. You're definitely removing some of the problem. Like delaying the problem. Okay? Okay. Thanks for all of you chiming in. Okay, so we understand the high lift devices. We understand the two different mechanisms that the high lift devices actually act to increase the lift coefficient or to delay the separation and increase the angle of attack at which your airfoil can operate, your wing can operate. There are many different types of these flaps and slaps. And I have some more things on the notes that I have uploaded on Blackboard. Okay, so we can do. Let's actually do this. Let me show you the video I promised, a YouTube video, or it is not a YouTube video actually. I promise, and then we'll be done with today. There are other mechanisms. This is worth mentioning as well. This is actually something that some people did some research with, like the direct barrier discharge. That, what was your name? Ben. Yeah, Ben brought up. That's something that you can definitely have. You're going to ionize the gas on top, which is going to introduce an electric field in the system. That's an extra source in the Navier-Stokes equation, an extra force going to push the flow down. But they can also have suction. Right? We can suck the body layer in. Right? When you're sucking the body layer in, there's no space left for the flow separation to happen. Right? Or we can actually have some jets. So doing the reverse of a suction, which is not a very effective way of doing this analysis because you are introducing some pressure as well, which is not a very desirable condition. So let's watch this video. This is on the high lift devices. And then that will be good. Do you see anything? Why doesn't it show? Oh. This is a very old video. It's one of the earliest studies that NASA did, at the time NACA did, on these high lift devices. This is like a flat plate thing. You can see the changes of angle of attack, how it affects your flow pattern. You see the separation here? It started at a very low angle of attack and gradually moved towards the leading edge. Right? The separation here was more sudden on a flat plate. I guess this is a very long video. I guess we can move. Let's actually see this part, and then do you see the flow pattern here? There are some flow coming in from down the bottom plate to the top, and we have flow separation here, but we have another streamline that is connected to the airfoil at the trailing edge. So we are essentially reducing the effects of flow separation. Let's just stop the video here, and it is already 6:42, 6:45 on that clock. So we didn't have enough time to start chapter 5, but chapter 5, we can start chapter 5 on Wednesday, but that's I guess I could have waited for the class to finish before turning this on. We will start chapter 5. Chapter 5 is going to be your last chapter of the Anderson's book. We will have a small discussion of flight mechanics, which we don't have a reference text for. I will just give you my lecture notes. And there won't be any problem that you need to solve from the flight mechanics part of the lecture, but you just have to understand the concepts, right? Or I mean, even if I ask you to solve something, it's just an addition and subtraction. It's not going to be a very hard thing to understand or analyze, okay? So see you all on Wednesday.